Actually, what are we going to talk about today, or what are we trying to do? First thing, before we talk about what we're actually going to do, it's very important to me that you notify me if I explain anything in a way that is not really understandable. So it's no problem at all to say, hey, please stop, could you explain this again, or yeah, could you speak louder, or yeah, could you turn this off? So it would be very important for me to communicate with me. And make this more a discussion. And what we'd like to do is, first of all, talk about the very basics of transforms, not theoretically, but applied to when you work with EMC. So the four basic things, which is translate, rotate, scale, which are the basic transformations that you use 99% of the time. We try something out, and then we'll go into some background details of what is actually going on back there and why the 3D system is not only applying to VDDB, but this is applying to every real-time 3D engine, maybe OpenGL or DirectX based, maybe Unity or Unreal Engine or whatever, because all these principles are the same everywhere. So we would like to talk about a little bit more of that mathematical background. It might be a steep ascent from what I'm trying to teach you, but I think if we go through it step by step, it should be pretty clear. If not, yeah, maybe there's some time afterwards and we can sit down again and look at it again. We will have then a look at how these basic transforms actually work in math. After that, we will have a look at VDD again and try out some stuff with some special nodes that you might know or might not know. For instance, the applied transform node, where you will apply transform to an object that is there already, but you apply it to just values, coordinates in space, which is a trick for many things. Also, what's a very important part of the whole thing is what is actually going on in the whole rendering pipeline. That's where we are with your aspect ratio, that's where we are with the view pin, the projection pin on the render, stuff like that, and how does it all fit together. And yeah, also these within nodes are very often not well understood what's actually happening in there. It's actually pretty easy if you can follow it step by step, but it's not so hard to get. And maybe if we have time in the end, we can have a look at some more nodes, especially when it comes to stuff like topography, which is a cool node, but we just use it. We have no idea how it works in the background. Usually it's not necessary to know what's going on in the background, but if you know how to use it, it's okay. And maybe even Quaternions. Have you ever heard of Quaternions? What's a Quaternion?
This is like a mathematical construct to rotate 3D objects in a 3D space.
A mathematical construct to rotate 3D objects in 3D space. Yes, it's a very generalist
numbers and so on.
Yeah. Actually, Quaternions are complex numbers on steroids. Have you heard of complex numbers? Where a number and then you have a real and an imaginary part. And Quaternions are complex numbers that they have three imaginary parts, which is pretty hard to grasp if you've never heard of it. It doesn't matter to us. We just need to know how to actually be able to use them because they're not so hard to use. We just need to know, okay, we have to convert things to Quaternions, take something in Quaternions and then convert it back to negative. Also, Quaternions are very basic to all the 3D engines, every rotation, the background is real, Quaternions. We'll see if we will get to there, if not, it's not. It's important for me that we can continue step by step and yeah, we'll see what we can do. Okay? Also, if anybody of you has a transformation problem or has a project where he has a thing that he never ever figured out, or he never ever figured out why it doesn't work the way it expected to be, we're open to that. So if you by incident have anything with you that you would like to share or show from a project from the past, sure, why not? Right. I'd like you all to start B4 because for the plain beginning we will just do a very simple patch together that oops. We will start from scratch with that. And does everybody have V4 on their computers and open? Great. For simplicity's sake, I'm going to use the EX9 rendering system, the old rendering system. Regarding transformations, it's almost the same in DirectX 11. Well, transformations are the same. It's just some nodes that are called differently, or there are some additional nodes that are in DirectX 11, which we can have a look at as well. But let's start off with a very basic setup that usually you start off with a patch, which is basically a renderer, EX9, and maybe add a group to it, so we have possibilities of more inputs. Yes, and please, if I'm too quick or at any point I'm jumping ahead, please pull the brake on me and say stop or slower. And what we also could do in the start is create an axis and grid object. There's an axis and grid DX9 2D object, which will help us to understand the space that we have here actually. And also just create a quad from the beginning. And I'll be going to start from the very basics now. It's probably stuff that you heard already many times before, but I think it's important to stress these things out because they may become later important later. First thing that you all know is as long as you don't apply any transformation to the renderer or any special things to your objects in the scene, you know that your renderer actually will have a dimension that goes on the x-axis from -1 here to +1 here, and from -1 down there to +1 for y up there. This is a basic fact that you know, and this object in the center of the screen, which should actually be a square, is not a square, it's a rectangle, because this renderer here has the funny property that what I just said about now, about the borders, left, right, up, down, will be the same all the time, no matter in which way my renderer is scaled. So the only time when my quad is actually a square is when my renderer is also a square. We'll have a look at that later, how we're going to fix that with the aspect ratio and what's actually a good idea to do. But just for beginning, leave it like that. Make your renderer a square. You can look up the dimensions of your renderer on the top bar, because right now it says for me my width is 400 pixels and my height is now also 400 pixels. So my renderer is actually a square now. And now let's create some transforms, and I would like to ask you to not create one of these transform nodes, like transform 2D or transform 3D, not these ones, but just the basic nodes translate, transform, scale, transform, and rotate, transform. Okay, so these are transforms that we can apply to our objects that are being rendered, and the funny thing about these things is that we can actually chain them together. So for instance, we could say, hey, instead of a scale, I will make a uniform scale, because I want to scale my quad now to a smaller size so that we have more space on the screen. And just scale it down. So that we all know, we have here a quad that is now smaller, and we can now add another transform to the whole thing. For instance, we could add a translate, which is more or less a movement of our quad, so we can shift it on the x-axis or the y-axis. So, for instance, if I increase my x value here, it will be moved out. On the y-axis, it will move along the y-axis. And in the end, I will apply a rotate. Rotation here I will do on the z-axis, because you probably know already, in a rendering system the z-axis is the axis that is perpendicular to your rendering plane. So you know this one here is the x-axis, from up to down is the y-axis, and the z-axis is going in this direction. In DirectX it's actually going into the screen, which is a very important property of DirectX. Yeah? We should talk about the coordinate system a little bit. Actually, when you're talking about reference coordinate systems, there are two types of reference coordinate systems. There are just convention. There's no reason why one is better than the other. It's not different. It's just saying, okay, in which direction do I point my x-axis? And they're called left-handed coordinate system for DirectX and right-handed coordinate system for many other applications and programs. Why are they called like that? Because if you take your hand and take your thumb, that would be your x-axis, then the index finger, which would be the y-axis, then the middle finger will point in the direction of your hand. And if you apply this to your renderer here, you can see the x-axis aligns with the red axis, the y-axis aligns with the green axis, so the z-axis must go into the screen. Understand? So if I had a right-handed coordinate system, it would be like this, that if I align my x-axis and my y-axis to the screen, then the z-axis would go out of the screen. So positive z-coordinates are behind the screen, negative z-coordinates are in the room here. That's one important property. But leave out z-axis for now. It's just important when I do a rotation around an axis, and that's what this node rotate actually does. It just takes the object where it is right now and rotates it around an axis. If you change the value here on the z-axis, you can see that it actually performs a rotation around the center of this coordinate system, around an axis which is actually going out from the center of the screen. So, and what you also probably know is that apparently it does make a difference in which order these transformations are being applied to our object. So we have these three transformations here now, and can anybody tell me what happens when you change the order of these transformations? So for instance, if I would apply translation first, rotation afterwards, and scaling at the end. And if I do my rotation now, maybe increase this one here. I didn't change the rotation and translation order, sorry for that. If I first rotate my object, then translate my object, and then scale my object, and perform the rotation now, rotation suddenly does not rotate around the z-axis of this coordinate system that I had before here. Does anyone have an idea why this is happening?
Is it the first thing happening before we translated it, then the whole translation got rejected?
That's a good point. Actually, it does matter what happens first and what happens afterwards. But I'm going to open a patch now which illustrates this a little bit better. For your information, I have some patches. I put some patches on the drive already on the transformations folder, which is on the network drive already. You can download them then from there. But usually after the workshops, whatever we are going to do in the workshops, I do the patches again, comment them to your questions that you had, and we'll put them up there again. So probably if you will look in there tomorrow or the day after tomorrow, they will be updated. So what we have in here now is just for starting to work with it, and you will get like a proper documented patch version afterwards. Okay? So. I prepared a little patch here that actually shows what's going on here and how to read all this. Because there's two ways, or for me at least, there's two ways to read these transformations and what's happening where and why that's not happening. I made myself the experience for a long time. I didn't really find out or didn't really understand, okay, what is the order, what's happening where, why is it behaving like that as it is. And I found it's always a good way to read them from bottom to top for some instances, and from some instances it's also interesting to read them from top to bottom. But I'll start with the transformation from bottom to top because I think this makes stuff more clear. You don't have to patch this right now. You can copy them and open these patches if you want to, but first just stay with me and try to understand what's actually going on here. I'll just undo this here and make my own. Oops. Because then it will be easier to understand. I made the same patch that we just did ourselves, but I just also made a special indication for the corner points of this quad, because actually a quad is consisting of 4 corner points that make up the triangles that the quad is being made up of. And actually, when we're doing transformations, we are only working on these vertices, these corner points of objects that you have. And you can look at it like that. If you create your quad down here, you will create, the program that creates the quad, or the algorithm that creates the quad, just knows, hey, I should create a quad that has a side length of 1. And that means if I create this quad in the center here, then this will be minus 0.5 on the x-axis and plus 0.5 on the y-axis. Here we got plus 0.5, plus 0.5, plus 0.5 on the x-axis, minus 0.5 on the y-axis, and minus 0.5, minus 0.5. So far so clear. Okay? Then we will apply a transformation. And actually, the first transformation I'm going to apply here is a uniform scale, which is a transformation that basically takes these coordinates values that we have and does a multiplication with a factor. It just takes the x-axis and says, okay, the value that this corner point on the x-axis has will be multiplied with a factor of here 0.5. So it will be probably half the way from it was before. Of course, the value that was on the negative side of this will also be multiplied with 0.5, which will be half the size, which will move towards the center. So scaling something with a smaller value will probably move towards the center, with a larger value will move it outward from the center. So this is the first transformation that we did.
Where's the address to the server?
Pardon?
The address to the server? Can you just have it?
172? Yeah, sorry. I did not mention that, but yeah. So this is the address where you can get this patch, which is in the basics folder. Okay, so this is the first step that has been applied to the object. We scaled it down. Second step is a translation. Translation is nothing else but moving an object or adding a value to the existing coordinate of the corner point. For instance, if I have this corner point here, which is now at 0.25 on the x-axis, and I add a value of 1, then it will be a value of 1.25. So that's actually what's going on. I'm adding a value here, and will offset the whole thing and apparently not only 1 point, but all the 4 points with a certain value, so we will end up somewhere else. And in the third step, I will apply a rotation, and this rotation will take place, or will be performed on the coordinates, on the points where they are right now in the universe. And the rotation will always be performed on the z-axis when I rotate around the z-axis and apply the rotation button. So, in the end, this is what the rotation does. So, when I think from it from bottom to top, it's easy to understand, okay, what's happening where? And yeah, this is a good start. Just for making this clear again, now if I actually turn this around, rotation and translation, let's have a look at this first. First I do the scaling, object will be in the center. Afterwards I will apply the rotation, which means on this very place where this quad is right now, the rotation takes place. And in the third step, I'm able to move all the points where they are right now to a different place in reference to the coordinate system. There's one interesting fact for you to know. Actually, rotation and scaling do not have an influence on each other. For these two, it does not matter in which order they are being performed. Translation, translation, on the other hand, does have an effect if you apply it before or after scaling. For instance, what's also a very annoying fact sometimes, if you, for instance, have your quad being translated first and then scale afterwards, the effect might be not what you would expect. For instance, I have my quad here and I'm translating it somewhere, and if I apply the scale afterwards, you can see that actually all the corner points move, because of course it will take the x-coordinate from here and will multiply it with the factor, so we will end up somewhere else. And especially this is something that very often through beginners, you have your object somewhere, hey cool, I just want to make it larger, and at some point it moves this way, but actually that's not your intention. So you should also be aware, okay, where do I actually put my transformations? And yeah, if you apply to some rules, like doing the scaling and the rotation first and then the translation afterwards, which means translation on top and scaling and rotation before that, that's a good thing to do.
I will copy it on the flashcard. I will copy it on the flashcard.
That's a good idea.
Yeah. Go on.
All right. One more thing to add is I deliberately now use translation, rotation, and scale, and not the transform nodes that you can find in VVVV, because for these nodes it's not clear to us if you don't know in which order actually these transformations take place. Actually, a transform node, if I take a transform 3D node here, this is actually the same as doing a scale, a rotate, and a translate. So that's the order of transformations that are actually being applied to an object when you are using a transform node. That you should be very aware of, because sometimes you just do some rotation here, pitch your roll, and then a translation, and maybe even add another transform node to it, and suddenly you have, when you do this twice, for instance, just be aware that if you do something like this, this is the same as doing these two things twice. And suddenly you have a translation and a scale and a rotate afterwards, which might have unwanted effects that you are not aware of or that you don't want. All right. Just a second. It shouldn't be working on. All right. This patch here is basically exactly the same as what we saw before. The only difference is that here I'm reading transformations from top to bottom, because this is also something that sometimes helps to understand what's actually going on. Because you can always see an object as an entity, yeah, that has been transformed or somewhere. For instance, if you have a compound object like a car. A car has 4 wheels, yeah, and these wheels are not in the center of the car, but they are on the locations of the car where they are supposed to be, on the side, on the bottom. So at some point you need to transform them to a place somewhere where they are at, and then in the end you want to move the entire car, and not every object by itself, and well, the car should stay together and not fall apart or move apart. So this is what you can do when you think with transformations that come from top to bottom. Whatever I have been doing here, down here. For instance, this is a quad that consists of the quad and my beautifully visualized corner points. I do some translation, rotation, scale, and at some point here I would say this object is finished and it's supposed to be like that, and it should not be torn apart anymore. Whenever I feed in some transform from top in here now, this would mean I'm transforming kind of the universe for this object. I would say, hey, now everything that comes in from top is like a hierarchical parent of the whole thing, and it will behave as it was one unit down here. So for instance, if I would take a translation now, and since this translation doesn't have anything that goes in here from the top, I can actually move it and it will move around the x-axis as I would expect. If I would apply a rotation here, this rotation would basically behave like I would rotate the whole universe for the whole thing. Because think of the car. If I take the car and rotate it around because it goes around the corner, of course everything that's attached to the car, yeah, will rotate with it. So applying the rotation will do a rotation on it. But what happens now if I, for instance, like change a wheel of the car, or maybe apply some super wheels which are bigger and a little bit outside? If I apply the movement on the x-axis here, the x-axis is not the x-axis that our reference coordinate system has, but its own x-axis, because the whole universe of the car was twisted in a way. So, oops. Actually, we've moved this so far. We should. I could, for instance, yeah, just use move the. Yeah, if I move this now here on the x-axis, I should probably also delete this rotation, then it's more clear. You can see, actually now the movement here on the x-axis is the movement on its local x-axis that it has. And the local x-axis does not align with the global x-axis anymore because the whole universe of the car was kind of rotated. Yeah? And many problems arise because people are not aware of that when they mess around with the transformation order, yeah, applying global transformation and local transformations in an order that is not really thought of, because you mix translates and rotates and translates and scales and stuff like that. This is the point where everything starts to mess up.
And actually, you even have like this. You just mentioned global transformations and local transformations, and something which transforms first and something which transforms second.
I think you should talk, because it's really hard to.
Something that transforms first and second, and the actually global and local ones, it just means exactly the same. Yeah. So if you have this matrix multiplication, you transform it from left or from right. You got it to be first rotated and transformed, things like it's actually all the same. We will go through it.
Yeah. The only thing is, I think, my opinion why VVV, why it's easy to mess up in VVV is because we don't have like this object-oriented way of thinking like you have from many other 3D softwares or from Photoshop even or After Effects, whatever. In Photoshop, it's like that. You can have like a folder where you have all your layers inside, and if you apply something to the folder, then everything that's inside this layer will be transformed the same way. Or in After Effects, or in the 3D program when you have like a compound object that consists of the hull of the car and its 4 wheels, then if you do the transform on the car, then everything will be transformed with it. And if you do it locally on just the wheel, then it will just happen to the wheel, but of course in relatively to the car. And in VVV, we have to take care of this ourselves. We have all these transforms. Actually, it's a good way of thinking of or a good practice to like encapsulate everything that belongs together in a patch, in local transform. So at some point you will reach a point where you have the transform input, and from this point on everything below here should not be cared about anymore, in the sense that you don't want to mess with the individual parts. It's just a big thing now, and this is the thing that we should do. Are you following me? Some eyes have question marks in them. Please, at any time. Yeah.
So is it always like, say you have a translate, rotate, scale, like add an entity, and then so as soon as you apply another rotate, scale, or translate on top of that, you're looking at 2 different entities.
It's a good way of thinking about that, yeah. Because as soon as you have like one of these hierarchies and you put something on top of it, it's like the whole universe around this object is being transformed. Of course, you can translate, rotate, scale again if you want to, but you have to be aware that as soon as you do this, for instance, if you want to just rotate this object again around its own axis, it might not end up somewhere there where you wanted it to be. That was a bad example.
Let's just not call it a universe. Let's just call it a car.
Yeah, let's call it a car. I think it's mostly easier to think of it like an object-oriented way of thinking. You have a car, and stuff that is attached to the car will go with the car when you move the car. That's the most easy thing way to think.
Yeah. So either you are inside a car, so you are a part of this car, yeah, and you are looking left or right, or this whole car, even with you, rotates left or right. Yeah. That's actually the order of the transformations.
Alright. What I usually like to do is like to patch a small example of these transformation hierarchies and where they can actually be of use. And my example that I like to do here is patching a little solar system where you have in the center of the universe the sun, and around the sun the Earth is rotating in a way, and then you have the Earth with the moon. The moon is rotating around the Earth, and it's easy to show actually these transform hierarchies and these hierarchical relationships between the objects, and what I mean is its own center of the universe, yeah, or its own car. So let's try this together. We're going to start from scratch. Right. So what we need first is a renderer, of course. Let's add a group. I will be using a segment for my sun, so a segment DX9. And I will increase the resolution so that it actually looks like something like a ball. And the sun is big, but it's not as big as our renderer, so I will just decrease its size by applying a uniform scale. And that's my sun, because we are living in the 15th century, or at least 18th century, we say the sun is the center of the universe. Great. Next thing I will do is I will duplicate this whole thing, because I don't have to patch the whole thing again, for creating an Earth. Of course the Earth is a blue planet, so I will just change the color to something blue, and of course decrease the size a little. Can you see this? Of course it's not only sound, but it's also the light that really distracts us. Okay. So can anybody tell me what would be necessary to make the Earth rotate around the Sun? Translate it out of the center of the universe and then rotate it around the z-axis, which is the center. Let's try. So apply a translation. For instance, I could move out my Earth a little. And afterwards let it rotate. Around the z-axis. And of course letting this be done by an LFO, which constantly changes a value, makes the whole thing a little bit more interesting. I've seen most of you are there already. Do quick thinking. Actually, what is the moon supposed to do? The moon is supposed to do exactly the same as the Earth is doing around the Sun. So the moon is rotating around the Earth, and the Earth is rotating around the Sun. So we can actually make a copy of the whole Earth thing. I should have renamed the whole thing to Earth as well. Oops. So I will create a copy of this thing here, because I have this scaling, moving out, rotating here already. That's what we need for the moon as well. I will rename this whole thing to moon and give it a different color. So. So, for now, my moon is rotating around the sun as if it was another planet. But actually, when you think about the stuff that I said now before, when you put something inside from top, a rotation from somewhere else, then you kind of move the center of its personal universe. As I would like to belong the moon to the earth, it's like a wheel belongs to a car, I need to have the same transformations that the car does to the moon as well. And if I feed it in from top, then it would mean the moon does all the transformation that its parent does, plus its own transformations that it does here. So, from where would I take the transformation to be put in here? From the Earth? You mean from here? From translate? Why is that? Can you explain why? That's right. I'll just decrease the scale a little so it's more apparent and make the LFO from the moon a little bit shorter. So, we did not take the uniform scale from the Earth into account because actually we want to be able to set the scale of the Earth and scale of the moon independently. Because right now we're taking the translation and rotation that the Earth does, which defines its position in space. And take this in here from top, which means that this is basically the center of its own universe. The middle of its car, the whatever. And put it in top here. Additionally, the moon will make its own scaling, translation and rotation around its center. So you could argue that at this point here, this is the center of the universe, and if I translate and rotate the center of its own universe, this is where the whole thing that's happening below here will happen. Take a minute and have a look at your patch and really try to understand step by step what's actually going on here.
I will say just the same thing in other words again. So when you are going down and down with the transformations, it's becoming more and more local. Yeah, like that you first relate the Earth and then you relate with the Earth. So it's becoming more and more local.
Exactly, yeah. At the very bottom you have the segment, which is just a definition of, well, a segment-shaped-like object that would be created in the center of the universe. But by applying all these transformations, you can get the system. So. Do you have any questions?
this is a, again, it's mostly quantization. So if this were an asset, you give some centralized set whatever. If you're looking at something, you only see what's complementary.
All right. So I think we have a very basic understanding now of how transforms and the order of transforms actually matter. And I would like to continue and talk a little bit about some mathematical background of the whole thing. But I will not use I will not use my slides right now, but I will go to the whiteboard. Martin, did we get some pens to write on this? Oh, yes. There is? Okay, very good. I will do some formal definitions and formal introductions of what is actually going on in space, because what's coming now is a little bit of vector mathematics, vector math, and it's pretty easy to start with. It will become a little bit more complicated later. Oops.
Yeah, you don't call it linear algebra at all, so you are not scared.
I'm missing a patch here. Where is it? Doesn't matter. This is something I didn't apparently copy, but I know where to get it from. Sorry. This is a patch that I copied from former node, which was happening in 2013. Oops. No, I don't think it was in 15. We should be there. Okay. Sorry for that. Oh yeah. That's what I wanted to show. Actually, what is a point in space and how is it defined? We have been doing this implicitly before already, but if I'm talking about a point in space, then I can define it in multiple ways, but usually what we do is we're using a Cartesian coordinate system, which means that we have a coordinate system that consists of three axes: the x-axis, the y-axis, and the z-axis. And if I, for instance, have a point that has position 1, 1, 1, or as in this example where it has position 2, 2, 2, it just means that we actually can come to this point by moving from the origin of this universe, from this reference coordinate system, one on the x-axis, one up on the y-axis, one back on the z-axis. And we arrive there at this location. So this is my point over there. I can describe it with a vector that I take from the origin of the space and move these three coordinates there. What is a vector in comparison to a point? Actually, a vector is basically what you see here, but just without any origin. That means every other vector that is in here, in this space, I will just open up another patch to illustrate this, which would be this one here, I think. A vector space is consisting of all the vectors that go into the same direction, but they don't have any origin. So everything in here is a vector that has the same properties, with length 1, 1, 1 here, and yeah, that's what a vector is. And the thing is, if you have a point in space and you add a vector to it, you come to a different point. You can add a point to a vector, you can add two vectors to each other to get another vector, but you cannot add 2 points. That's a different thing. 2 points, adding 2 points doesn't make any sense. You can add a point in a vector, you can add 2 vectors, but you cannot add 2 points. Alright, let's do some maths. What actually happens when you do a transform? And we're coming to something that is apparently used, it's used in every 3D engine because it's so fast. I just have to save my files here so that I have something to comment afterwards.
So again, this vector is generally like a movement. It's a movement, let's say, from point to point. Yeah. So the movement itself doesn't have any location. That's why a vector doesn't have a location. But it can move a vector and move a point to another point.
I'll just use my board now because I don't find something that way. Put something in front of the projector so you don't see it. Just take a little. Yeah, that's it. I'm going to repeat something that I said before already, but this is important so that we understand what's coming next. So, if we have a coordinate system, I'm working in 2D now. I'm omitting the third dimension because it makes stuff more complicated. In the end, it's just easier to have one dimension in the 3D space. So, for instance, yeah, if we have a point here, this is the direction on the x-axis, this is the direction on the y-axis. That makes you come to this point. So, actually, a scaling operation, as we saw already, is just a multiplication of these two factors with the scalar, which is a constant. So, it means scale plus x by scaling from x and y scaling from y. Usually points and vectors are written down in math like this. And as we can see later, it's also okay to just write them down like this. Why it's like this, I will come to later. Because it makes a difference when working with direct x and working here. Okay, if I want to come from a point to another point, for instance here, I could say this is just a vector that goes in this direction. So we got a vector that describes this point here, and we got another vector that describes this a way from some point to some other point. So actually, to arrive here, I call this x prime and y prime. To arrive here at this point, we can take this vector and this vector to arrive right here. Because this root here is x plus x prime. And this root here, since this is a negative value, we go down, is y plus y prime, which means we go this direction up, and since this must be negative when it points down, right? This plus a negative value will arrive at the truth value. Pretty simple. So, for rotating rotation becomes a little bit more complicated. Rotation can be defined by a coefficient matrix, which usually looks like something like cosinus, an angle, sinus, sinus, minus sinus angle, and cosinus multiplied with x and y. So now I threw something at you that you have no idea of, which is probably the case, which is matrix multiplication. Matrix multiplication is a thing that's very, very handy for all these operations. Because in the end, we will only work with matrices. And that's why I need to give you a whole introduction to matrix multiplication. So this is going to be the dry part of the whole thing, but if you get this, and if you really try to get it, you will have a great tool for afterwards understanding what's actually going on in the background. The cool thing is that all of these operations, or at least let's say scale and rotation, can be written down as a matrix. And why matrices are cool? Because afterwards you can multiply all these matrices together to have a resulting matrix that has a combination of all these operations that happened before inside this matrix. So for instance, if I would say I would like to scale a point or scale a vector first equal to a point and rotate it afterwards, I would first make, for instance, we would say, okay, let's have scale and then a rotation. You would have an operation for that, I would just call it S, and we have an operation for that, so R. We can multiply this together, and what we get out from it is a representation of these two things together. So it's called SR. And these things can be represented with matrices. So,
sorry for interaction. You are probably missing some note, and it's not important. It's just for visualization of the vector. Yeah, and if you want, I can give you the flashcard. It's on the flashcard, but it's not important there. Please go on.
Right. Now this is the funny part. Taking back a slide. Can you take this again? Back again? So, before we get into matrix multiplication and what we actually need for doing this is what is actually a matrix. A matrix is basically just a way of, well, a clever tool that mathematicians invented to solve linear equations. Don't worry, we're not talking about linear equations. I just want to give you some information what actually a matrix is and how they are being worked with, because we will see that this is actually very handy. Matrices are represented as squared values, which means they are represented in a square. For instance, we have a matrix of size 2 by 2 that contains just two values in rows and two values in columns. So there's 4 values. This would be a 1 by 4 matrix, which would mean we have just 1 column and 4 rows. Yeah? A 3 by 2 matrix has 2 rows and 3 columns, and a 4 by 4 matrix has. Matrix can be of any size. Yeah? Everything that has to do with computation in math and stuff like that will, many things will be represented in matrices, and this is something that we can use here because we also can write down points and vectors as matrices. For instance, if we represent a point or a vector in space, it will be a matrix of size 3 by 1. Please.
What is the mathematical convention to go from top to bottom, like A, B, C, D, from top to bottom, or like line for line?
To answer your question, I have to jump in front a little bit, because there is two conventions, or there is several conventions. Actually, it doesn't really matter. It only matters to know actually what, well, for the matrix itself, just from a mathematical point of view, it totally doesn't matter. It's about the things that you want to represent with the matrices, where it starts to matter in which way you write it down. For instance, what we could do is we could write down our points as a matrix like this, as a 1-by-4 matrix, which has 1 column and 4 rows. And we could write down, for instance, like this is my x, y, z value, and maybe another value here. Or we could write it down like this. If we apply an operation to this afterwards, then of course it does make a difference. We will see in a short while why this is the case. How these values are written in the matrix. So you can see here I got 1 1, 1 2, 1 3, 1 4, and over there I got 1 1, 2 1, 3 1, 4 1. So it's a totally different. It's exactly the other way around. It's rotated by 90 degrees. In matrix speaking, this is called transposing matrices. But we're jumping ahead. Right. Let's talk about how we can actually work with matrices. And matrix multiplication is the main tool for doing stuff like that. Because if we can, usually we represent, for instance, vectors as 1-by-3 matrices or 1-by-4 matrices, and these operations like scaling, rotation, translation as 3-by-3 or 4-by-4 matrices, as we will see, and we need to multiply those together. Actually, how does matrix multiplication really work? Well, what you do is the following. You need to have a look if your matrices actually have compatibility. That means you cannot just multiply every matrix with every other matrix because sometimes they don't fit together. And it's easy to look that up in a way to just see, when you write them next to each other in the multiplication, to see if the last element, well, the rows and the columns of the next one actually have the same dimension. If these two match together, then you can multiply these matrices, and you will also get an information of what dimension your matrix will have afterwards, which is defined by the outer values here. So, for instance, if I had two matrices, u by v, x, y, z, and a, b, c, d, e, and so on, how would you multiply these matrices? What you would do is, you would always take the first matrix and go in column-wise. You go from left to right, and the second matrix you go from top to bottom. So, what you would do is, you would take the first value of the first matrix and the first value of the first column of the other matrix, multiply those together, plus the second multiplied with the second, plus the third multiplied with the third, and the result of this addition of these three multiplications would be the resulting value in the first resulting value in my output matrix. So there's plenty of multiplications going on because you have to do this for every row, for every column. Yeah.
Maybe I don't get it, but I understand the UA.
Yeah.
But I don't understand this V.
Sorry, there is this.
VY. Shouldn't it
It should be VB.
Sorry, it should be VB, definitely. I made a mistake here. No. Definitely. It should be VB. Very well. Okay. So this way. So first column and first row. First row and first column is the first value in the first row and first column. If I take the second row and the first column, it will be the first value in the second row and the first column. It means x by a plus y by b plus z by c. Z by c, yeah? Would be, because it's the lower row and the first column, it will be in the lower row and the first column. Got that? Okay. The same we do for every other column and every other row. So I take this one by this one, and the result will be in the first row in the second column. If I take the second row and the second column, it will be the second row and the second column. So, only leaves the last row, first row, last column will be the value of this first row of the last column, second row, last column, second row, last column. Okay, that's how matrix multiplication actually works.
So just going back to these rules, yeah, you can actually see that so that to be able to multiply it, here has to be this same number of numbers like here. Yeah. So it's like 3 numbers. So this has to match.
Yeah. This is this red 3 by red 3. Yeah.
So we're having like say like a 2D vector there, yeah?
Yeah.
And what is that? Is that a 3D scaling we put on there? Or
We will come to that. In there, we will do all the operations that we would talk about. Yeah, everything that has to do with transformations can be represented as one of these matrices, which is the cool thing.
Yeah, but can we like say like a 2D scaling?
Mhm.
2D scaling have only 2 rows A, B, C, D, E, F, or is scaling always like a 3-dimensional?
I'm coming to that right now. So, for instance, if you had a vector, well, 2D point in space, and you had an operation that looks like this. You have a matrix that has over the diagonal 2 scaling factors, and all the other values are 0. What you can do then is you can multiply x by the first scaling factor plus y times 0, which is 0. The result will be x times the scaling factor. Yeah? So for the second column we have x times 0 and plus y times sy. So the result will be x times x and y times the scaling factor from y, which is exactly what we did before here. So this is just the first information how this matrix multiplication actually works. So, small example, we got a point in space which is at location 2 and 1. We want to scale it by 3 on x and y axis. So the result will be at 6, 3, which kind of makes sense because this is 3 times 2.1. So if you can imagine this in a coordinate system, you have a point 2.1, and after scaling it with these factors, it will end up somewhere else. Okay, so that wasn't probably that hard. It's just this matrix multiplying thing that you first have to get. If you got that, suddenly we got a possibility to represent an operation like a scaling operation with a matrix. And the cool thing is we can do something very similar for a rotation. Rotation, the matrix looks a little bit different. It doesn't have scaling factors, but it has cosine and sine and sine and cosine factors for an angle. So if I want to rotate a point around the z-axis with an angle theta, for instance 45 degrees, you could take the x and y coordinates, apply these cosine and sine functions to it, and do this matrix multiplication, and you will get an example that I currently did not finish. Sorry for that, I need to finish this in my slides. But again, we got a 2 by 2 matrix that has the same size like the scaling matrix. Which means these 2 matrices could be multiplied together, like I said here. We have a scaling operation, we have a rotation operation, and we can afterwards multiply these 2 together to get another matrix that has some letters in it, but these 2 letters represent both 2 operations in one compact form.
Yeah.
Question? Yeah?
As I know, for transformation stuff in 2D, we need a 3 by 3 matrix, right?
I'm coming to that. That's what's called homogeneous coordinates, and actually this here is the reason why.
A generally cool thing about this is when it's 2D or 3D or 4D, it's very similar. It's like the same mathematics behind it and about the same matrix transformations.
I'm starting here with a 2D space because we have less numbers, but it's basically the same operations. So, we know from before that actually a translation, which is moving a point, is just, well, a point plus a vector, and it will end up somewhere else. So, we got we got a point, we got a vector, and we can add x with A and Y with B, and we get a result. The question is just, can we somehow represent this in a matrix so that we actually be able to combine these transformations? And this is where your thing comes in. Can we somehow do this? And the answer is yes, of course, with a mathematical trick. Because what you can do is you can say, hey, I just say my plane, my 2D space that I have, is actually just a subspace of a 3D space. So I just add a dimension, and it's easy to understand. For instance, if you would think, hey, this table here is all the space that I have for my points here, but actually it's just another subspace of the 3D space that is around here, then we can do this with 3 by 3 matrices, and we just say that this plane here is at C coordinate 1. What changes here for our matrices is the following. Instead of having a 2 by 2 matrix, we have third dimension for that we take into account, and we just say Z is 1. The same is true for the rotation. We just take our 2 by 2 matrix, put it on top in here, yeah, and down here we add a 1, we add a 0, and we can just continue to work like that because, yeah, it's just math. We just need to multiply matrices. And the cool thing is, like that, yeah, we can also, I forgot to say that, when we get a point in space, this point is of course on the table, on this plane, so the Z coordinate will also be 1. We just get another dimension in here, but it's the same point basically. And we can apply all these operations like before with the new matrices. And what we also get is another matrix that has this form. We don't add our translation values if we want to make a translation in these two values in here, but we can add them down here, because if you think of it, let's do this multiplication of any point with this matrix. It will be x times 1 plus 0 times y, which will leave it out, plus t times 1.
Just to explain it a little bit more, we are still in the 2D space now, but we have a
three-dimensional representation of our 2D space.
Yeah, yeah. And so the bottom line is just the translation.
Yeah.
Because before, when we had these numbers, there was just a rotation and scale. We didn't have the translation there. That's why we use like one more row.
Yeah, one more dimension. So what you can see from this output is apparently the translation, the vector that we need to translate, we can put down in here to get a result that says x plus this factor and x y plus this factor and c coordinate 1 again. So it will be possible to have a matrix that represents a translation that we now can use to combine translation, scale and rotation. We are still in 2D space, but we do this trick of bringing it into 3D space to be able to make all these transformations. And in the end, what we get from these transformations is a point that has 3 coordinates. The last one will usually be 1, but we know that x and y will be like if they were in 2D space.
Can we go back to...
Sure.
Yeah.
This one.
Yeah, so like down there where we put tx and ty, like I have on the next slide, we have 0, 0.
No, this is the scaling matrix, yeah, where the scaling factors will be here on this diagonal.
Yeah.
The translation matrix will look like this, that on the diagonal we always have 1, and just down here we have the vector for the translation.
Why do we have always 1 in the diagonal?
Because otherwise this result will not be there as we want it to be. Because we want to have x there and y not there in the first year. Yeah. So y will be multiplied with 0, x will be multiplied with 1, so it will be there. And 1 multiplied by this thing here will make this appear here in this addition that we get. Yes?
So would it be scaled then as well as transformed? Like the ones were 3s? Like this matrix be like scaling and
if you
transforming
would
our
change
values?
something in here,
Yeah.
probably something would come out that you would not expect.
Okay.
I'm not sure yet right now if actually this would just scale the whole thing or do something completely different. But actually I think it would be a scale because
it would just take, yeah, it would be just scaled all.
Oh, so certain things in that matrix do different things. So like the first 4 numbers on the top left, they do the scaling, and the 2 bottom ones do the translation.
You could think of it that way, but if you look back, you can see that actually scaling is here and also the rotation is in here in the first 4 elements. So actually they do have an influence on each other.
Okay, but the translation is always down the bottom.
Translation will always be down here.
Okay.
That's right. At least in our way of thinking.
We're actually coming with such transformation matrices that they do what we want them to do.
Yeah. In the end, we just want to move, rotate, and scale. We know how this works. We apply this matrix form because it has certain properties that are really, really cool for us because we can just multiply them together. And in the end, we will get a result that when we transform a point with certain matrices like this, we will get a result where all these transformations are being applied to this point. And it will be in a space that is 1 dimension higher than we actually want to have. We did this now for 2D space with 3D coordinates. And now if you think the next step actually is totally possible, mathematicians don't care about this, to take 3D space and add another dimension to it. Of course we cannot imagine this anymore because we cannot imagine how a 4-dimensional space looks like, because we can, it's not in our world of thinking. But if you think of 2-dimensional space in 3D space, that's totally possible. And you know that 2D space, a plane, is just a subspace of a 3D space. For mathematicians, it's no problem to say, hey, 3D space is just a subspace of a 4-dimensional space. And that's what they actually do. If we do this whole thing for 3D coordinates, you will get all the slides afterwards. So I will just correct some errors and it will be online, so no problem. If we take a point in 3D space and just add another dimension, a 4th coordinate, then we have a 4-dimensional coordinate. What we have here is a translation matrix that is just 1 element bigger. We have translation x, translation y, translation z. On the diagonal we have only once. Every other element will be 0. The same goes for scaling. Scaling has just 1 dimension more. It will have a z factor in this diagonal in there. But how about rotation? Well, since we are in 3D space now, it's not just one axis that we can rotate about. In 3D space we can rotate around the x-axis, we can rotate around the y-axis, and we can rotate around the z-axis. So there's 3 different rotation matrices. If we would want to rotate around the z-axis, you can see again these cosine and sine factors that we have in here. But for the x-axis, we just shift it down a little bit. And for the y-axis, we shift it down once more, or we kind of separate this. So that actually works.
You don't have to repeat, or you don't have to remember like what is what. Yeah, just know that it is there.
Cool thing is V4 does everything for you in this sense. Yeah, you just need to know, hey, this is rotation, and this is rotation around one of these axes, and it's a scaling, and it's a translation. All right, and just to show you that actually all of this, what I told you right now, is actually really happening, we will do something that you probably have not tried before, which is we will look inside a transform.
So this behavior that you can combine these transforms together, it's like super cool. It actually allows all the graphics to be just transformed once. And for example, like after in the presentation, we will see how it goes on the graphics pipeline. That we just take one transformation as a camera and we use it like for all the scene.
Yeah. So I'd like to do this with me because this is something where we really can play around now and actually see exactly those things that I just showed you. Oops. Take any of these transforms, like translate, rotate, and scale, for instance. And there's a node which is called get matrix. And get matrix is a node that takes as an input a transform
it's also useful if you just want to know what is happening with your transformation matrix and what is actually there. Sometimes you can find numbers like not a number or unlimited or things like it.
So, what we have here, get matrix takes as an input a translate, and if you from get matrix from the output pin take a thread and just make a middle click, it will automatically create one of these 4x4 matrices as we have just seen right now. And now you can start with playing around with these values to see what's actually going on when you do a transform, what you actually are creating. And as you can see, all these values, these factors that I just showed you, they actually appear in this matrix down here as the translate values. Same thing goes for scaling. It just becomes totally weird when you're doing some rotations, because rotations, when you rotate around the z-axis, you can see that's actually quite a lot of values that will be changed here.
You can see it's actually the same like in 2D. Yeah, this rotation around the axis. It's just the axis that we edit like as one more. So yeah, it's actually 2D rotation.
And if you're really daring, you can also take any other transform. Now, the nodes that are of category transform can be represented with such a 4x4 matrix. And even though we just now had translate, rotate, scale, there is stuff like perspective, there's stuff like look at, there's stuff like whatever, shear, vertigo. killed my VVV. So I just killed VVV somehow. Alright, so you just found out about a new world that's behind of transforms.
That's why the rotation matrix is, I mean, the six values changing, the others are usually like 3.
Rotation matrix has the property, and that's something that I will talk about in a second because I got this open already. When you look at rotations, actually you got not one rotation going on, but 3 rotations going on. Because what you can do is you can only rotate around one of the axes. That means you can rotate around x-axis, you can rotate around y-axis and z-axis, and all of these will have a different rotation matrix. So what actually is the case when you have a rotation matrix, or a rotation transform node, what looks like a rotation around 3 axes here, and one operation is in reality 3 operations. So what we have here as a rotate node is actually this. I will make this clearer by not showing the axis. We have a rotation around the y-axis, we have a rotation around the x-axis, and we have a rotation around the z-axis. And all of these happen in a certain order, which is a big thing if you don't know about it, because suddenly when you rotate stuff in space, it doesn't behave always the way you want it to behave because of this order. We will talk a little bit more about this later. But this one node is basically like doing first a rotation around the z-axis, then a rotation around the x-axis, and a rotation around the y-axis, which means if you rotate around z and x-axis and do a rotation around y-axis afterwards, of course, first they have been rotated in another way, and in the end around the y-axis. So there is also some kind of transform hierarchy, which will lead you to some problems, which are also known as Gimbal Lock, for instance. Have you ever heard of that? Pardon?
What's it called again?
Gimbal Lock. Yeah. This happens when when a rotation axis from around the y-axis, for instance, lines up, if you turn it 90 degrees, with another rotation axis, and you cannot differentiate between these two axes anymore. We will have a look at it afterwards, so I don't want to jump ahead. But let us just analyze what we just found out with all these transforms that we have. We have rotate, we have scale, we have translate. And actually, get matrix, let us have a look what's happening inside. Now what happens actually when we have a scale and a translate and a rotate operation. I'm coming back to what I said before and what Martin just mentioned. When you put several transformation in one order, you can have a look at the transformation matrices at any point. You can say, okay, let's have a look at the translate transformation matrix. Let's have some value here, some value here. Oops. The result of this translation I could scale, for instance. So you can see this value changes here now. Actually, scale and translate does not influence each other because they are on a different, they are on different values in this matrix. And if you do a rotation afterwards, yeah, do some rotations around several values, this will be the result of these three operations. Each matrix by itself defines the operation. These matrices can be multiplied together to have another matrix that represent both of these operations, or if you have another one, that one matrix that has all the information of all the former transformation inside. And when you think about this, this is really great, because think of some object that you want to put in space. Take, for instance, take our car. A car is made up of an object of many different vertices in space, and actually when you do a transformation on the car, you need to do a transformation on all these vertices, and this can be thousands of vertices. If you just have one transformation matrix, 4x4, and each of your vertices of your car needs to be just transformed or just multiplied with all these, with this one matrix, it's a rather simple operation. Of course, there's some multiplications you have to do, but it's far less work than if you would have to do all the operations before on each vertex, which is a great thing. And that's why matrix multiplications and transforms are used in every 3D engine, because they are so efficient. I just opened up my patch from the beginning with the quad, if you remember. Because if you are really interested in what you would actually have to do to transform one or several points, I did all this manually just for you to look at. Actually, I just activated the result of all my calculations that I did and put them into a segment that you can see here, overlaid. And as you can see, if I wanted to do a scale, I would need to multiply every value with the factor. If I wanted to translate it, I need to add the value of translation to all the points. If I want to rotate the whole thing, I would need to do all these sinus and cosinus function things to all the points, and I need to do this all successively, which is a hell of a lot of operations. These matrices are far more efficient because you can represent it, you can represent all these steps in one 4x4 matrix. And that's the reason why matrices are cool, and that's the reason why we did this hard thing of trying to understand on a Thursday afternoon at a node where you're supposed to have fun and not do math. Okay. He pointed out this issue with rotations of matrices, that actually when you perform rotations are actually also in a certain order, and since we are only rotating around these three axes, we are kind of limited. Because, for instance, if I would say I would like to rotate a point around some certain line in space, that would be not easily possible using just these three axes. I can tell you why. And for this, I have a patch prepared that actually MicroD was showing in one of his weekend workshops. I just adapted it a little bit. That shows this problem very well. Just don't have a look at the patch first, just have a look at this image here. Because what we are actually trying to do here is we have this funny monkey head, and what we have on top of here is two positions where this monkey head has a certain rotation in space. Yeah. In the first rotation he just looks up, and then the second rotation he looks to the left. And when you look at the transformations that we are doing here, what we're doing, we're just morphing between these two values of rotation that we have here, yeah? For x, y, and z, x, y, and z. And when we morph between these two values and apply these to just a rotate transform, you will see that actually this monkey doesn't move in a straight line. Actually, this monkey here, it moves when it does the rotation in some kind of arc and not directly. Because it's simply not possible to just interpolate between these two rotation states with these angles. We call them Euler angles. Euler was the one who made this. And this is the point where quaternions become nice, because quaternion, this high-level representation we were talking about earlier, allows us to do just that. And if I'm correct, yeah, I will go in detail about this in the end when we have looked at some other nice things about transformations. But these Euler angles, they allow these quaternions, they allow you to do an interpolation for rotations without, well, twisting somehow, which can be a problem, especially when you would like to have. This is a common problem if you have known 3D programs and you know you want to animate cameras in space, and they have a look at some object and they go to another place and they have a different rotation then somehow they don't do this direct rotation, but sometimes they just twist around, which might be a big problem in animation. Jörg, do you know this problem? Yeah? How do you deal with it usually? So you manually kind of correct for these things. Okay.
Mind that quaternion is not a part of transformation matrix. Yeah, like in the transformation matrix, we only had the choice to use these angles and the rotation about single angles. Yeah. So that's why we can't really say, let's combine it all together and use it as it is.
But this is just a preview for later things. So, are you still with me? Still motivated? It's cool. Good. So, we kind of did all the basics. Quite something already. Yeah. Something that I said in the beginning already, these conventions. The thing is, if you really became interested in the whole topic and you look into textbooks of math and theory about computer graphics, you will often not find this representation that we had right here, but you will find a representation that looks like this. Sorry. In this representation that we used here, in the beginning we wrote down our vector and then had our transform matrices. And we had, for instance, our translation components down here. What you usually find in textbooks is something like this, where you have the vector in the end, but not in a row, but in a column. And all of these matrices, they are kind of rotated by 90 degrees. So what was down here in this row is suddenly moving up here. This is the way that most textbooks and also other 3D engines like OpenGL deal with the whole thing. You just have to know about this. It's totally the same, it's just a different notation. The problem is, it's just some theoretical background. What you've seen here right now, you've used this get matrix and set get matrix node to look in what happens inside a transform. When you do a translation, for instance, you could see that the values down here changed in this row. This is because you're using a notation where we say the first element is down here, up here, the second element is here, the third is here, the fourth is here. What you usually find in textbooks, or when you look in the internet, you can find stuff that the first element would be here, the second here, the third here, the fourth here. Just rotated by 90 degrees, for some reason. It's just a convention thing. It's like, okay, I decide the z-axis goes into the screen and not out of the screen. Now somebody just decided this, hey, we're going to need to do it like this. And since VVV works with DirectX in the background, and DirectX has this convention here, I told you the whole thing with these things here. When you look it up on the internet, you will often find stuff like this. And this is just a warning for you. So, hey, we're not talking about different things. It is the same. It is just written in a different way. That's the difference. That's what I wanted to point out. Okay, you think you need a break? No? Wow, hey, we're doing math here and they're still with us. Cool. Yeah.
You will explain the quaternions under the rules, how it works mathematically.
I will not explain it here because first thing is I'm not too firm with them. The second thing is I don't think that we will have time for this, but we can talk about it afterwards. And we'll just show you how to do a Quaternion interpolation. That's how to use them, but not how the theory in the background works, because that would be too much.
Theory is in the background. It's quite hard. Yeah, it's like not really simple. So yeah, but using them is very cool.
Yeah, definitely. Right. So we now know how actually objects are being transformed in space, and the other big topic about rendering is what kind of transformations do you have to apply to the renderer to get on screen what you want to see. And we have to talk about some spaces here that I can also demonstrate with a patch that I have prepared and hopefully will find.
This will be actually quite similar to the first example when we were like joining transformations together and doing this sun and earth and moon.
Oops. All right. I guess all of you have already used a camera on a renderer, did you? So you connected the camera to the view and the projection pins of a renderer and stuff like that. Okay, because let's do it from scratch. I think it's more easy to understand or easy to follow when we do this all together, because then we have it step by step. Please start again by creating a renderer and putting again a group with some axes and grids. And the quad on it. Okay, we're all there. So, what do we see here? We have our basic renderer that goes from -1 to 1 on both axes. We have a quad that is lying in there, and this quad actually was defined to have a side length of 1. So each of the sides has the side length of 1, and this is a definition. So we could say this definition or this model is defined somewhere. Or for instance, if you had not a quad but like a 3D model that comes from a 3D program, then this model would be defined in this 3D program and it stands for itself. It's just the definition. So we could say this object here at initial creation is in model space, or its space is the model space. But at some point we are putting this model into our world, and at this point we do a world transformation. That means we take it from model space and move it somewhere in the world, and now it is in world space. This is what happens as soon as I would place this in here and do some transforms on it. Just using this transform node here. This is just for you to understand. So, the quad itself, the way it is defined, is in model space, or object space is sometimes called. Are there different words for that as well?
Depends if you're in OpenGL or DirectX. It's the same.
All right. So we apply some transform on it, and suddenly this thing here is in our world. So that is why it is in world space.
Only the transform puts it there.
Now, as soon as we put the model in the world, actually it is, well, originally it's in the center of the universe, it's in the origin of this world, yeah, so it is already in world space there, but by applying some transforms on the model, we apply some world transforms, and it will find its way in the world. So it's just about, like we sit here, yeah, we use it there, and I sit here on this table. By moving somewhere else, you have a different place in this world. Yeah. So we haven't talked about our view on the world yet. This is something different that we're coming to now.
I'm still the same object, but I'm like moving in the world.
Yeah. So we didn't talk about how we view this world. This is something else that we're coming to now, because you all know probably that actually this renderer at the moment, when we didn't define anything, has this certain property that actually it has a side length of 1. And also, for instance, if I would, I'll just exchange this for a 3D version. If I would move my object, my quad here, on the z-axis into the screen, it should become smaller, we would expect. But no, it doesn't become smaller if we move it back. And also, suddenly, after it is behind z value 1, it will disappear. Also, if I move it below -1 on the z-axis here, it's gone. So apparently, the space that we are looking at has some borders, because if we move it out of these borders, then it's not there anymore. We'll talk about this a little bit later. Let's talk about the view that we have on our world. Actually, the view on our world that we have is defined by this -1 to 1, -1 to 1 border. And we can actually move our view in this world. And this is what the view matrix of the renderer is for. Here you get a transform input, which is called view. And you can just go here and add, for instance, a translate on this view matrix and start moving your camera in this world. Try this out.
See that you're moving all the objects.
Yeah, it's not one object, but it's your view on the world that is suddenly different. And try this out. Maybe you will notice something which is kind of weird. What's the weird thing about this? Exactly. If it goes right, it goes left, and if we would want to go left, it goes right. So have a look at the values that you can see here. For instance, I'll just reset my y-axis. I would suppose, or I would expect, that if I would move on the x-axis into the positive range, which is this direction, that my camera, my view would also go in this direction. But apparently, it does exactly the opposite. It doesn't go to the right, it goes to the left. Also, if I would move my camera on a positive y value, I would expect to view the world from top, but no, actually, I'm going down. What the hell is going on here? This is also one of the properties that most people are not aware of when they work with 3D system, which is the property that actually we are not moving a camera in the world, but we are rather moving the entire world in front of the camera. The result is almost exactly the same, but if we are not aware of that, we do exactly the opposite here as we would expect. What can we do to fix this problem? There is an operation which is called the inverse of a transform. And there's a node for this, which is called inverse transform. And the inverse of a transform has the property that it will take one of these transformation matrices and will create its inverse, which is a mathematical operation how to find this inverse. That's actually when you take a matrix and multiply it with its inverse, then you will get the so-called unit matrix, which has just ones on the diagonal.
It's not that you would just do something with the numbers, like putting one divided by numbers or minus or something. It's a little bit more complex, but it's like very straightforward defined.
Yep. I have an example here about the inverse of transforms. For instance, I have this translate matrix, and this translate matrix, when I look at it, you can see that down here you got the translate values that I put on top of here. If I take the inverse, you can see that these values are now exactly the opposite of these values that I had on the other side. And the funny thing is now, when I take a matrix and multiply it together with its inverse, then what I will get is the so-called unit matrix, which is a matrix that has just ones in the diagonal, and that means anything that is multiplied with this matrix will be the same as before. It's like when you talk about ordinary math, when you have a value multiplied by 1 is again the same value. Or when you have a multiplication by 5, and you wanted to know what's the inverse of 5, it's 1 divided by 5. So 5 times 1 divided by 5 will be 1. So this is kind of the inverse principle. Alright, so if we wanted to have the expected result for our translation here, so positive x values should be actually moving the whole thing to the right, then we need to take the inverse. Please take the source input and not the transform input, because of course this is just an ordinary transformation matrix and we can multiply other transformation matrices with it. Okay, so this is the first thing. This is more or less our view on the world. We're actually not moving a camera in the world, but we're moving the entire world in front of the camera. And everything that's in this cone, in this cube here that we have, that's from -1 to 1, and from that will be rendered. All right. Then we've got another input, the projection input, and the projection input has the property that it's actually defining the way we view our world, because there are now several different ways to do some kind of projection. Because right now we have some kind of parallel projection. That means if you would say this screen here is my viewing plane, and actually what do we see from our world? When we see our world, we do some kind of projection from 3D space to 2D space. We do a projection on a screen, like it's happening here. Like when you take a photo, you see a 3D world, you're taking a photo on a 2D plane, and you will have it in 2D afterwards. This is exactly the same what we're having here. And now there's different ways to do this. When you have the camera, you usually have different lenses on this camera. You have like wide angle lenses, you have zoom lenses, and all these properties of these lenses define how you will look at your world and how the photo will look like. And the projection, or the kind of view that we have at the world right now, is a so-called parallel projection. That means, if you would say, this is my screen here, you would have like viewing rays that go out in the world, and all these viewing rays are parallel to each other. This is the reason why, when I move my quad a little bit back on the z-axis, it doesn't become smaller. It has the same size. It's kind of unusual for us to think, because we, in our ordinary visionary system, are used to things that are farther away become smaller. This is not the case here, but we can correct for this as well. But this is just one way of doing this.
It's like we are looking for from very, very long distance, from actually unlimited distance. But then when we are looking from very, very long distance and objects move closer and farther away, they actually don't change their size, because the rays are just like...
The rays, it's like you're having a super zoom.
Is it always parallel projection?
No, we can correct for this. We can do two things. Actually, there's a node which is called Ortho Transform, which also does a parallel projection, but it allows you to do one thing, because when you look at these inputs that it has inputs which are called near plane and far plane. Because what we saw before is if I moved my quad a little bit out, further than c coordinate 1, it would disappear. So apparently this cube that we are describing here has some borders, and everything that's inside the cube will be rendered, everything that's outside this cube will not be rendered. Here, this ortho node has a near plane and a far plane, which allows me to define these borders. What is actually in the view that can be rendered, and by defining it with minus 100 and 100, it means that we have a lot more space to do this. And just to prove this concept, I have it now connected to the projection pin, and if I move my quad now out to say 99, it's still visible, but it's now smaller. But if I move it over 100, it should be gone. So suddenly the view cube that we're looking at has become much bigger, and we can see this whole thing.
You can actually again have a look at this at the output from the ortho matrix in the get matrix. Yeah. So that you will see what the ortho matrix actually does, and it just creates a transformation matrix that actually takes this minus 100 to 100 and scales it down to minus 1 to 1, and then it's the same like it was before.
Yeah.
For the cube.
So actually you're totally right. What I said right now is we are extending this cube, but actually not the cube is extended, but the whole world is being compressed into this cube.
It's again the same principle. Like we are not moving with the camera, the world is moving like with us.
So like we did before when we didn't move the camera, but we moved the whole world. With the ortho view, we don't extend our view in the world, but we compress the world so that it fits in our cube of side lengths minus 1 to 1 and so on.
So it's actually 200 by 200 the cube? The cube from minus 100 to
No, the cube is always minus 1 to 1, but the world, stuff that is farther away at position like 100 will be moved to the cube, into the cube. So it will be kind of compressed inside this cube.
We just care about the Z, or what's this? Z.
So we care about the Z, and it's like from minus 100 to 100, so it's 200D.
We just scale the Z kind of, and we leave X and Y as it is, just now.
So when you look at this, actually the Z scaling factor suddenly becomes very small. It's 1 and 1 for X and Y, and for Z it's really, really small.
And the 0.5 under it is that it moved, because we have to move the center of our new space, and we have to scale it.
Yeah, but actually the orthogonal projection is something that you probably don't use it often. What you usually use is the perspective projection, which is a projection that relates to us much better than the orthogonal projection, because it's a central projection where you, as we are used to from our world, see objects that are farther away, smaller, and it all has to do with. Just write this down. Imagine that this is here our eye, and in front of our eye we will have some kind of viewing plane, and from our eye, we will send viewing rays into the world, and if I detect an object here, like it's a tree, for instance, it will be projected here on the screen with this size here. If the same tree would be farther away, you could see that actually the viewing rays for this tree that is farther away will be then projected on the screen much smaller. This is the reason why objects that are farther away will appear smaller on the screen, or smaller for us. So, and perspective is a node that creates a transformation matrix. We will not go into the details here of how this transformation matrix actually looks like, but again, it's a 4x4 matrix. that has all these properties. If you want to, you can have a look at it here. And suddenly we have a view on the world that somehow it's hard to see on the projection, but somehow you will have a view on the world that kind of looks like of what we are used to and what we usually expect. And also here, this perspective node has as an input the field of view, which is more or less the zoom factor, whether we have a wide angle or a zoom view on the world. And also we can define again a near plane and a far plane, which define where the borders of what is being rendered and what is being seen by the renderer is. So again, actually, the stuff that is being rendered apparently needs to be multiplied with this world view and of course also with the projection view to be on the screen afterwards. So everything here that we had before created in our world, set in our world, will be multiplied with this view, all the coordinates that we have here. So, because if I look at the world from a different angle, from a different position, of course I will see different things. Some things I will not see because they are out of my view, but if I change my camera, they will be in the view again. And if they should appear on the screen, of course, they should somehow relate to this view that I have on my world. And the projection then, in the second step, tells me what is my view on this world. Is it more like a zoom view? Is it more like a wide angle view?
So we have three transformations now. One just transforms the object, and we have two transformations on the camera. One thing I will actually show, it's like if you don't use any view, if you don't use the view matrix, and you only, let's say you don't even transform the object, and you have only like something which doesn't really show anything, let's see.
That's the coordinate system?
Like that. It's drawn without anything when it's just like this. Oh, okay.
I have this axis in grid 3D, which has this. So
Yeah.
Disconnected.
Okay. Sometimes you just don't see there anything, and you just wondered because like without the perspective there was something, with the perspective there is nothing. The thing is that the perspective actually moved it into the camera. So if you want to see something, you just translate. It's no translation. Now there is translation, and if you just move it to 1, it will be the same size again.
Yeah. You have to imagine this like this, and I have a patch prepared that will show this or demonstrate this a little bit better. When we use perspective, we kind of not have this box anymore that we look into the world, but we have like more a cone, like a pyramid, that we can see. Our field of view is defined by how far we can see. And this pyramid has a front end and a back end, the near plane and the far plane. And the near plane is usually set to a very small value in front of the camera. And when the camera itself is in point 0, and the coordinate system also is in point 0, but our view on the world starts a little bit later behind it, of course we won't see anything. So we have to move the camera back so that we see again the stuff. Is there a question?
This perspective matrix, this is like 4x1. The space is like linear. And if we want to recreate a fisheye effect, how will this matrix will look like?
You can't really create a fisheye effect because a fisheye effect is a distorted transform. You can only do this in post-processing on the 2D. No, actually there is options to transform or warp the entire space.
Yeah, well, really creating a fisheye effect means that one line, gets this shape. Yeah, and for example. So what you could do is to interpolate each line with many vertices and then make it kind of a spline. But generally, fisheye is not a linear transformation, and we are working just with things that don't make any curves. Everything what is in here is like rotation or scale or moving, but it don't break this.
Yeah. All right. So apparently, there's only one thing missing: this annoying renderer not keeping its aspect ratio when we resize the whole thing, and that's why the renderer has a hidden input. Well, the pin is not visible, but it's there for the aspect ratio. And the aspect ratio is nothing else but a scaling transform that, if applied correctly, scales everything into the right position. Which means there's a node which is called aspect ratio transform. And the good thing is, our renderer actually tells us down here it's backbuffer width and backbuffer height, which means from the width and the height and pixels we can derive actually the aspect ratio of the whole thing. And all we need to do is feed this in here, aspect width connected with actual width and aspect height with actual height. And this is one of the few moments when doing a feedback loop without a frame delay is allowed. You can just connect this to the renderer, and suddenly, no matter what screen size you have, you will always have a quad that's visible, and that's actually a square.
This aspect ratio is just provided for us by V4, and it's there to make our life easier.
Yeah. And you said you usually have problems with the aspect ratio and objects that are...
No, it's more when I have some geometry in the patch somewhere else, and I want to, for example, I have a quad in the top of my patch, and I want to have the right proportions. And yeah, somehow I didn't know if I should transform it there or in the end, because
let's say you have a screen and it has some aspect ratio, the screen itself. And then you have some object, let's say it's also like this size, yeah. And the object like this size has a circle in the middle. Let's say it's a flat. So you have to display this object. You actually have to use this size plot, yeah, and put the texture on it, so that the circle stays circle. But if you take this and put it into this sphere or into this rectangle, then it will be scaled down. Yeah. So that's the second part where you have to use the aspect ratio again. So if you are using some some object like in the scene, you have to have it in the correct size and locally transform, yeah. And then you have a global transformation on the view. This is like on the camera.
So it's two different things. First, you should always apply the aspect ratio on the renderer, because usually you will not have a squared renderer, which is the thing. And then when you're working with objects that are not squares, of course you need to adjust the squares to the aspect ratio of the content that is displayed on the squares. But you should never, you should never not apply the aspect ratio to the renderer, but to all your objects, because this would be like the opposite of what's reasonable.
So I choose the aspect ratio in the end of the renderer and the aspect ratio transform on my quad, for example.
On your quad, if you have a texture that is not a square but a rectangle, then of course you have to like scale the quad to the aspect ratio of your texture.
It's a very usual problem, because then you just put it so that it looks all okay, and then you put some rotation on it, and it starts doing these crazy things. Yeah.
And that's a different node, right? One on the bottom is another aspect ratio node than the one I choose for my.
Yeah.
Yeah. Okay.
Like this has a correct scale. That's part of object transformation. And this has like correct aspect ratio, which is also once again on the scale, but it's a part of the view. You can actually see that from the aspect ratio that is down there. Yeah. If you again put it into the get matrix thing, you will see that it's only like a scale over it. So.
Okay. To visualize all these camera transformation stuff that we just did now on the renderer, I created a patch for you to study. I will just show you this. This patch here has two renderers. It's called camera frustum. Frustum is actually this view cone that we have on the world. There's a name for this. And actually, this top renderer here is just a renderer using a camera. The camera is just a module that makes it easy for us to set view and projection in a more convenient way, just with the mouse in the renderer. And I can move around here and have a look at the world. And in this bottom renderer, I have like an outside view of the whole thing. And what I used here for is nothing else but a box that is being transformed with all the transforms that this camera gets. It has the view transform multiplied with the projection transform multiplied with the aspect ratio. Actually, I took the inverse of the aspect ratio because it's supposed to go into the renderer and not into an object. And then when taking the inverse of the whole thing, then you will see what actually the camera does see. So it's nice to demonstrate what actually happens when you remove all these transforms. Because in the beginning, you will have this view cube. Actually, this cube, I think it has side length 2 in depth as well. So this is what will be rendered. What's inside this cube will be rendered in this world. And when you apply this view transform, then this cube will go to the position where the camera actually looks at the world. You can see it will always look at the moment at the center of this universe. And this is my position of the camera. second step would be I would apply this projection matrix to this cube. So I will see what actually will the camera see. And suddenly, wow, hey, one of the ends of the cube will be very small, the other end will be very large, and it looks more like a pyramid, like a cone.
I just draw that I'm showing the same thing in 2D. Yeah, so from the rectangle, it just did the same, that it squished one part, so that you see this one as closer and this one is farther away.
Exactly. And this plane here is now the near plane, and the other plane down there is the far plane that we can set in the perspective node. And since this was a cube before with side lengths of 1, as soon as we apply the aspect ratio to the whole thing, you can see that it suddenly will shrink a little bit. Suddenly, the view cone, I'll move a little bit in here. You can see that it's actually now also a rectangle, and since this is dependent on my renderer, if I stretch the renderer, you can see that actually the view cone also is being stretched. Don't be distracted by the diagonals that I didn't remove from this view cone. This is just from the cube for rendering purposes. So actually, you can see also with the renderer, we just have a few transformations that are being applied, well, to the renderer. Actually, it's being applied to all the objects that are being rendered. And they're just multiplied one after the other, and this is then the end what will be rasterized. Rasterized is the last step in the pipeline, when every object is being transformed so that our camera somehow fits into this world. Then we will make a 2D image from these 3D objects. So for each pixel on our screen, we will find the color of the object that is being displayed behind the screen. So that's basically how each rendering pipeline works. And if you got this, you got a lot. You got hopefully a deeper understanding, and you can really start having fun with all these things.
Will we have a look inside the shader? How it is actually applied?
We could do this in the end. I would just like to show another nice transform that can be really handy, which is the so-called look-at transform, because then also this concept of inverse of a transform becomes interesting again. So this patch here that I prepared for you as well, just as, again, this explanation why we have to use the inverse on the transform to really well. But it also has this node called look at. Have you ever used this node? Did you ever use this node? Look at is basically a shortcut node that allows you to define a position in space and another position in space where to look at, kind of to get a vector. It can be pretty useful for cameras. I'm at position A and I want to look at position B, and what does the transformation look like to do this? This node does it for me. And this node is meant to be, now when I activate this, it's now on the renderer. This node is meant to be fed directly into the view pin of the renderer. Yeah, so I don't have to do anything here. It's just one point, another point, and also what's necessary when you look from one point to another point, it's not completely clear where the up vector is or where's the upside, because you just define a line. You could look at it this way also. Yeah, so it's not clear in which direction to look at. But don't care about that. What's nice about this look at thing is that it can not only be applied to the renderer, but it can also be very nice to do some transformations on objects. For instance, I did a little patch here that, oops, doesn't work, okay. Where this look at is used to look from one direction to another direction for a few objects, which is a nice transformation and a nice effect. So I have this ball going from left to right, and each of the objects just always looks to this ball, which is exactly what this lookup transform does, because we have the position of all the quads, we have the position of the ball, and we just want to have a look at it, which is a nice effect. And to be able to use it like that, of course, you know now that since it was meant to be sent into the view pin of the renderer, we need to take the inverse if we want to apply it for real life. And that's exactly what I'm doing here. What you can see here on the bottom left is the quad and the axis, which is basically this spread of quads up there. I just define this lookup transform, which is made up of position 1, which is x, y, and z coordinates. The x coordinates are defined by this linear spread, so I have them like aligned next to each other, and I move them back in space a little. And the other position is being defined by well, an LFO that is moving, when I scale it up a little bit, on the x-axis, this sphere from the left to the right. So I just need the x position because this is the position of the sphere. I don't apply any y or z position. This is my point where to look at. Take the inverse of this transform, and that's all that you need, well, to make these quads and coordinate crosses look at this ball, which is kind of a nice effect. And if you know that you need to take the inverse, then it's all you need to know.
With this inverse and transformation order, that's exactly the same that can go into quite a mess quite fast, yeah? Because, well, transformation order, it's you multiply it from the left or from the right. You know, you try one thing, it doesn't work, so you try the second thing. Okay, that's it. You try to put the look at matrix straight ahead to the object. You realize, okay, this is not it, so I will try the inverse. Yeah. But then you are just doing this, and you have a wrong transformation order, and it's becoming to be complicated, and there are some things like moving on, and that's why actually it's good to know the theory behind and to be sure about it when you use it.
And when talking about the theory behind, I completely forgot one of the very important nodes that you might not have used until now, which is just this multiplier of type transform. Does anyone use this node? And because multiplier transform is basically the same as when you chain up some transforms this way. For instance, the translate, a rotate, actually, when you have two transforms that are chained together like this, it's nothing else but a multiplication of matrices, as we have learned. And this is what this matrix also does. It just takes one transform chain and it takes another transform. Whatever, let's do a rotate again. And the output will be another transform. So, why should I ever be using this when we can do this anyway by just chaining them up? That's the question. The thing is, sometimes it happens that you will get a transform from somewhere, for instance from a motion tracking system. For instance, if you ever worked with the new OpenVR or this VVVV OpenVR pack, where you got Oculus Rift or HTC Vive and you got these hand controllers, you will get directly from the nodes a transform that is always, well, in their own local coordinate system. Wherever you stand, this HTC Vive does it to have its own coordinate system, and you will get these values. But if you want to move the whole person in your virtual space along with all the hand controllers that you have, for instance, if you teleport to some other place, then you want, of course, to continue to work like you did. But that would mean, as we have known before, or as we have learned before, that we need to put our transform in from top because we want to teleport ourselves to a different place as a whole. That's what we did before. And if you get it from the node directly, we have no way of putting something into from top. And this is where this node comes in very handy. Because when you have a look at this like this, just imagine that this part here cannot be influenced anymore, and we have no possibility to put something in here. Actually, what I would like to do is I would like to apply some transform on top of here, but for some reason I cannot do this because it doesn't allow me to do this node here. Then this node here becomes very handy because it allows me to just take this whole transform chain and put the transform that comes in here from the left right at the end. So it's like this is basically the same thing. Going in up here or going in down here is the same thing. The good thing is sometimes you cannot go in up here, but this node allows you to do this.
Again, V4 is just like making our life easier by having there this input pin number 1 every time. And it also has like a nice order of transformations, so we don't usually care about some order of transformations. So that's why we usually don't do it.
Yeah. Also, another very important note that I didn't mention yet.
We always get 4 times 4 matrices. It's not like
as soon as you get a transform here, it's always 4 by 4. This is the convention, and this is not only it's not VBV's fault. It's every 3D engine works with that.
So I get the data and I can.
Yeah.
Like you can work with 3 times 3 transformation matrices when you are transforming just vectors, like normals on the graphic card. Where you got some shading on the graphic card and you start transforming the normal, so you are actually not moving it anywhere. Yeah, you are just like rotating it or scaling or something, and so then you only need 3 times 3. But you generally work with like 4 times 4.
Also, another node that I didn't mention yet, but is also very important when working with transforms, is the apply transform node. Who doesn't know this node? Okay, actually, until now, when we were using transforms, for instance, we had a quad and a renderer and some transform. You see that at this moment, the quad defines itself where its vertices are, and the translate will just translate the whole thing. And we don't have any influence on the vertices, what to do with them, and we don't get any coordinates out of it. Which sometimes is a problem, because sometimes we have like a vector input from somewhere. Think of Kinect tracking. When you got skeleton tracking going on the Kinect, what you will get is the X, Y, and Z coordinates of all the joints that you have on your body. And these are just coordinates where you got X, Y, and Z values as a vector. And sometimes you would just like to apply a transformation to these values to get out values again. And this is what the apply transform node is for. Because it has 3 inputs, X, Y, and Z. Oops. And nicely they're named untransformed. And it has a transform input. And what you get out is X, Y, and Z values transformed. So, what does it do? Well, for instance, if I have the point 2, 1, and 0, we could also show this in a renderer so that it's more clear. Maybe if I scale this down. All right. And sorry, I'll just make some X's. So I'll just take these values also as a translation for my quad, just that we actually see what's going on here. So
when we move it by 2, it's actually away from the minus 1 to 1.
Yeah, it's outside. Okay, so this is my point in space, and now I have here the coordinates. I could apply this to this one here, but I have no way of getting out the coordinates again. What I can do now is I can apply a transform that I get from somewhere, translate, to these coordinates. It's like taking this vector applying this matrix multiplication that we did before and getting the result out as a vector again. So for instance, if I move this whole thing by -1, then of course we can see that actually on the x-axis we moved this whole thing by -1. And this can be really handy because sometimes you just have the tracking data from somewhere not available as a transform, you got it here as coordinates, but you want to apply the whole a transform to the whole thing. For instance, think of a point cloud that you want to let fly around your hand. Yeah, and you actually want to have each coordinate of your point cloud, and you're having a hand tracker from HTC Vive or whatever, and you want to apply all the transformation that you do with the hand tracker on these coordinates and get it back out as coordinates again. Then apply transform is for you here at help because it does exactly that. I think here, when we do it like this, inside the quad or inside the whole rendering process, all these multiplications will be applied again, but we don't get access to the coordinates because this all happens on the graphic card. Like this, we can do the whole thing on the CPU as well and get the coordinates back again.
For example, you want to create a line. You know, line has sometimes transform in pin or not, I don't know. But if the thing doesn't have transformation in pin, you actually have to use exact positions. And this way you can get the exact positions, for example, for the corners of the quad.
Yeah. Okay, to finish up the whole thing, there's one more category of nodes that are a little bit different in DX9 and DX11, but they relate again to the things that we did before with the camera view and perspective. These are the so-called within nodes. Heard of these? There's a node which is called within projection, within view, which is the DX9 category. In DX11 it works a little bit different, but they're called the same way, within projection layer and within projection view. And to explain these, I have to open up my camera patch again that I had before. Or what is also always a good idea is open up help patches, because usually these transform nodes have very good help patches. And now as you get some background on how this thing works, they really help you. I'll just take the camera frustum. All right. So, now I'm doing the following. In my normal world that I have here, I will place a quad. Quad DX9. And this quad, when I look around, is placed in this space. And as you can see, as I move my camera, I can look at it from all the sides. And what happens now when I use this within view transform as a transform on this quad? Suddenly, it is gone. Now it's not entirely gone, it's just not visible. But if I move a translate in between here, translate, transform, oops, and move the entire thing a little bit back from me, you can see this quad is here, but apparently everything that I do with the camera is being ignored by this quad. What the hell is going on here? Well, actually, this within view node is, to be honest, not really a transform, but more like a hint to the renderer to say, hey, as soon as this quad is being drawn on the screen, please ignore the view transform that you got here. So that means the view transform is responsible for, well, how we look with our camera at the world. And we tell it, hey, ignore this transform matrix that you get from this view, then it will always be drawn like in front of it. Yeah? Relative to the camera. It will always stay there. It might even be possible, I didn't try that, but it might even be possible to visualize this thing here. No, since it's not really a transform, it's also dependent on this renderer. And
we're actually saying to the renderer that this object is already within view.
It is within view, so please ignore this view matrix that you get from the renderer. And the counterpart within projection is basically the same thing, but here it also tells not only ignore the view, but also ignore this projection matrix that you have, which has the effect that, again, this quad that I have here, if I move it back and forth, it's again in this cube that is between -1 and 1 inside. So every depth information, every projection information that might be in this projection matrix is ignored as well. And this can be very handy to have these nodes, because if you have something within view, you can easily, for instance, make like an overlay, like a head-up display kind of thing. For instance, if you get a game, you move around the world, but there's still stuff, buttons that you want to have always visible with you. Within view is the way to go, because it just renders this and it ignores the world. It's just not relative to the world, but it's relative to you, to the camera. That's why you use within view.
And within projection, where do you need that?
It's actually also like about aspect ratio. Yeah, like when it's within projection, you know that you are always in -1 to 1 rectangle. Yeah, because like we can actually try it. I hope I'm right. That this
actually it's not working like that in DX9. I just noticed it's a little bit different in DX11, because in DX11 I think one of them ignores the aspect ratio as well, and they work a little bit differently because you don't have them as a transformation that you put in from top, but it's more a node where you put in layers, like in here. Yeah, in this area, put in some layers, and for these layers that are connected to this whole thing, the view matrix or the projection matrix are ignored.
Okay, that's good.
Per group.
It is per group or per object. You can apply this to an object as well. You don't. So in
Now we do it to the quad, but we can also feed it to the group.
in DX11 you do. In DX11 I can show you. There should be a help patch of this within projection. Yeah. In DX11 it's like that. This little scene has this segment that is defined here. The segment has a layer output, which you would send to the renderer, and this within projection node takes the input from here as layers, and everything that comes in here will be within projection. So that means as soon as I move my camera, the segment here will always stay relative to the camera. And on the other hand, within view, apparently I need to translate this again. It looks the same, but you have this projection going on as well. So if you move it further away or closer to you, it will still be there. You can enable and disable this. But within projection, I think there's something you can configure also. Yeah, it has this preserve aspect node, which allows you, when activated, and if there was an aspect ratio node somewhere, or maybe not with the.
I said that I was just wondering what's the difference in use.
To be honest, I have no example for you right now. But Yeah, there you can see it. I have now applied the aspect ratio to the renderer so that everything will be rendered in a correct way. But since when I say it's within projection, I still rely to this one-to-one principle, but I could tell him to also preserve the aspect, so it will also have the right aspect ratio. Okay, since we're coming to the end of our workshop time,
Maybe you can very quickly show some quaternions or some example, just how to use them.
I would say, so if you're still having some brain power left, we can have a look at the quaternions and how to use them, and yeah, to understand them is a little bit too hard for now, but yeah, I'll just open up this patch from MicroD again, and because there we get something that helps us understand this problem. All right. So, problem is when transforming one object in space with a certain rotation to another location in space with a different location, we want to have like a direct translation to this whole thing, a direct rotation without having these strange lines or strange spaces that we have to walk through. Usually we define a rotation with using these three rotation angles, pitch, yaw, and roll, which are the ones that you can feed into a rotate node, rotate transform. We have the X, Y, Z, which more or less relies to pitch, yaw, and roll, rotation around the X-axis, rotation around Y-axis, rotation around Z-axis. Now, if we wanted to create a quaternion from these angles, there is a node which is called Euler, quaternion set vector, which is basically a transform from these ordinary rotate nodes to a quaternion. What is a quaternion? Well, a quaternion is this complex number that has three complex parts and a real part, and we had a discussion about this yesterday, because actually this quaternion is representing in a complex space some kind of vector with a direction and also an up vector. But what we were discussing about, I said it's not possible to directly derive the real vector from these values that we get here. And you said yes, it is possible.
Yeah, actually the direction is there. The direction is there, and if you have it like normalized, that's the thing. Yeah. If you have it normalized and you take first three like components as a direction, then you can like rotate according to this direction. But you have to change the length of the angles and the length of the W. Yeah.
But basically it comes down to this. As soon as you have a quaternion, yeah, either you're a genius or your brain shuts off. No, you just need to know, hey, we got angles in here, what we get out is a quaternion, and quaternions are super cool to work with, and then we can do some interpolations. For instance, there's a node which is called SLURP, which is a spherical linear interpolation. Let's see in the help page.
It's like
spherical linear interpolation, yeah. Which allows you, if you have like one rotation in space and another rotation in space, to like directly morph between these two. A LURP is an operation that morphs between two targets, you can say. You define these targets. If you say, okay, well, you can control this interpolation by saying, hey, if I'm at position 0, I'm in the one direction. If I'm position 1, I got the other direction, and everything in between is right in between somewhere there. So if I got these two vectors in space and I'm at position 0.5, I would get like this vector in between. And the rotation that is being done is basically done on a complex sphere. That's what I read. I didn't really understand. But this complex sphere allows to do these rotations directly without going some funny snake lines. So actually, if we wanted to do interpolate between these two positions, we need to convert these two to quaternions. We get two different quaternions, that we feed into this slurp, quaternion 1, quaternion 2, and in here we can specify, hey, where in between this interpolation am I? So if I'm at 0, I'm at this position, if I'm at 1, I'm at this position, and if I'm in between, at 0.5, I'm at the interpolated position in between. And when you got this, you get a quaternion again, and this quaternion you can feed into a rotate quaternion vector node, which gives you the transformation matrix that contains, well, the orientation of the object as a matrix that you can work with again. That's the whole thing that you need to know. So also, if you don't have any idea how quaternions actually work internally, this is one way to apply them. Because in the end, when you get a quaternion, you apply this quaternion to this rotate node, and yeah, you can apply these afterwards, usually as ordinary transformations.
So the most thing from this old patch which actually interests you now is this small bar right there, yeah. Like getting the Euler transform, getting quaternions and using spherical linear interpolation and making the rotation matrix from there.
Yeah.
With the linear interpolation, it's pretty simple. You can make like a linear interpolation from one point to another point, which means on 0 you're in one point, and it got linearly goes to 1 where you are in the second point. The same is with rotations.
Yeah, that's one way to work with quaternions, and why quaternions should be your friends, also if they sound scary. But if you really want to know something about these things, MicroD made a weekend workshop which you can find on YouTube, which is exactly about these things. Actually, I copied this patch and modified it a little bit, and it takes like 2 or 3 hours, and it goes deep into this topic. So if you're really interested in this, this is the way where you should continue. Well, so somehow we managed to get you through the afternoon. Oops. And have reached an end. I hope it was kind of interesting for you still to get some background information and how to work with these things, because as soon as you got a feeling for this, how this actually works, you make much fewer mistakes, which of course helps you tremendously in working with the target. Yeah, so I hope you had some nice new insights in this whole area. If you have any questions in the future, right now this week we are around. Well, you're leaving today. Well, I'm around. You can just come back and ask me. Yeah, use the forum. Forum is very nice, full of helpful people. Just don't be scared. And thank you.